So in the last class, I was talking about potential energy. So we have seen that this chapter regarding energy. So this energy is associated with our kinetic and potential energy because we are talking about only mechanics. So in mechanics, we have two varieties of energy. One is potential, one is kinetic. So we were talking about potential energy, which is the energy uh, like a body or a system possesses because of its configuration. Today we will talk about kinetic energy. Now, uh, to say about kinetic energy, kinetic energy is the energy that is associated with the motion of that object. So it happens when there is a motion in the object. Now we can see one thing here, that we know that energy is deeply related with the work done. So in that case, work done also we have seen the work done is force dot displacement. So if force is along displacement, so in that case the angle between them will be theta, will be 0 degree, and that's why you will get that W equal to F into R or F into X, you can say. Okay, so whatever is favorable to you. Now the thing is that we will derive the expression for kinetic energy. So to do that, we have to take use of the force equation. We know that force is basically what you say, responsible to change the state of any object. So if any object is at rest, when you will impart a force on it, the object will change its state, though it is having a laziness inertia, but then also it will change its state and it will move with some certain of velocity v. So before imparting any force to this object, the velocity of this object was 0, but once the force is acted on this, the final velocity will become some quantity. Let's say it's a v. Okay, so your final velocity will become v. So the change in velocity is 0 to v, right? So one thing we can see, one thing, that the velocity is changing from 0 to v, and I know that the force is also dependent on the mass, because force means the transfer rate of your momentum. So one thing you can write here nicely, that is your force equal to mass into acceleration, whereas your acceleration is nothing but your dv by dt. So once you go a little bit deeper into this differentiation, you will see that we can write this equation like this: dv by dx and dx by dt. So we have substituted something. So instead of dv by dt, we are writing dv by dx and dx by dt. Now why we are doing so? Because I know that velocity is velocity is nothing but your change in displacement by the change in time, right? So velocity is dependent on displacement. So that's why I have taken this thing, this dx I have involved here, and I can write this equation like this. So this is basically, in differentiation you will see this thing. So you can say like dx is gone and it's dv dt, but actually it's not like that cancellation. But yeah, like you can write this thing, okay, because it's a proper function. So once you write like this, so you can easily find one relationship, that is your m. Now you know that this dx dt, this term is basically your v, right? So I can write, instead of this, I can write this v dv dx. So look this carefully. So instead of dx dt, I have written here v, and dv dx is as it is. So one thing we can say that I have got right now till this much, that is my force is equal to mass into v dv dx. Okay, now this term is nothing but your acceleration, right? So your acceleration is your dv v dv dx, right? Okay, now what we will do, we will not go into this thing, and we will take only this portion. Okay, and we will write from this, we will write, so this dx I will keep this side, so I will write this f into dx is equal to m v dv. So you can see in this equation I have taken dx in that side, this side. So what this equation means actually, so basically this equation tells us that to do dx, like if you change like a dx displacement, like if there is a displacement of dx in some object, when you apply some force f, so your f dot dx, so that is what actually, this is nothing but your work done, right? So this is your work done. So the work done will be equal to mv dv. So dv is what? The change in velocity, and v is what? The final velocity, or the velocity at that time. Okay, so like this is the instantaneous velocity, so the velocity at that time, it is representing this thing. So this is instantaneous velocity, this is the change in velocity at that moment when you are imparting a force f, and because of that force the object is moving with a displacement of dx. Okay, so now the thing is that this thing is basically the instantaneous thing, that means at that moment what happened. But I want to know the total thing, like the collective behavior, ki what is my total work done if I increase the velocity of the object from 0 to v, that I was telling you in this case. Okay, so in this case the object was at rest, I am giving some force, object is achieving some velocity v, so I will do where what, I will just integrate this thing. So one thing you can see that this thing is nothing but your small work done, right? So I can write this is as dw. Why dw? Because like if w is my f into x, when the force and displacement is in the same direction, so my small infinitesimal work done will be force into small infinitesimal displacement, right? So this, you see, this means small quantity, so this is small work done for small displacement. That means to make a displacement of dx which is very small, infinitesimal, we have to do a little work, that is dw, which is also infinitesimal work. So instead of this I can write this as dw is mv dv. So my total work done will be, so what I have to do, I just have to integrate this thing, so that will give me the total work done. So integration here also, and this place also, integration is something like addition, like to what you say, to arrange all the pieces of puzzle, to like arrange all the pieces of puzzle together to make the whole picture. So like I told you already that differentiation slices the function, it breaks the function into pieces to allow us so that we can see the small portion of the function, how the function looks like when we break that. And what integration does, the opposite thing. That means like when you have a small fragments of a function and you add everything, then you get the total function, and this differentiation is doing that. So before the integration does that, and before the integration I was getting that infinitesimal work done for infinitesimal displacement. Now I will be talking about the total work done for the total change in velocity, that is from 0 to v. So what I will do, I will write here from 0 to v is the limit, like I am changing the velocity from 0 to v, and here the work done is happening like total work done. Okay, so the work done at first was 0, and then totally I have done say w work. So I can write this as w is equal to, so this is very easy integration. Once you know integration, it will be just like your blink of eye. So that will be basically bring this formula. So for now this formula is vital for you. Okay, the derivation you can learn later on also, but the derivation is important to understand the thing, what is happening. So this is how we have come to a conclusion that the work done to increase the velocity of some object from 0 to v is half mv square. Now that means it is half mv square. So like say so something was at rest, and now what I have done, I have just given some force to it. So at first the velocity was 0, and now the velocity is velocity becomes like v. So that means how much work, so I have to do something, right? Like I'm giving some force, that means I'm transferring my energy to that thing. So how much energy I'm giving it? So I'm giving it half mv square. Okay, now let's say a different situation, like let's say the object was already moving, but the object was moving with a little velocity, let's say v1. The object was moving with it, and then I worked, like then I give some kind of force to it, and the object is now moving with v2 velocity. So the velocity has increased. That means like I have given the work done, right? I have given the work. So how much I have given? So at beginning the velocity, like the kinetic energy for this portion was k1. Okay, and k1 was how much? That was half mv square, v1 square. And now the kinetic energy has increased because I have added some of the energy, like I have added my work to the initial energy, that was k1, and now it has become k2, which is nothing but your half mv2 square. So I can say that the k1 plus my input work done, that is my transfer of energy, is nothing but the final one. So I can always write from this thing that or I can write this as w is equal to k2 minus k1. So this I will get half m v2 square minus v1 square. So this thing is called work energy theorem. So it's just for the name, you know this thing is like normally logically it is very easy. Like I have a like $5 and somebody has given me $10, so now it's $15. So I can always write 5 plus 15 is equal to 5 plus 10 is equal to 15. So I can always write like that. So this is called work energy theorem. Okay, so this is nothing but your, let me change the font color. Okay, so this is work energy, my god, okay, energy theorem. So this is our work energy theorem, which tells that if somebody was moving with velocity v1, that means its kinetic energy will be k1, that is half mv1 square. And then if I work some, like if I transfer some of my energy to it, that is w, then the final energy will be the addition of my given energy and the initial energy it was having before. So basically this is it that you need to learn about kinetic energy, which is nothing but your half mv square. So what is v? V is the velocity at that moment, like when you are measuring the kinetic energy. Now in the last class I was talking about the potential energy, and we have seen there are two kind of potential energies basically we will be going to encounter. The first one is your gravitational potential energy, GPE, which is nothing but your m g into h. H represents the change in height. Okay. And one thing we have seen also, mechanical potential energy, that is basically for spring we have seen. So for spring we have seen that potential energy is half kx square, right? Basically we will be dealing with this in our next topic, and the next topic is the transfer of energy, like how the energy convert one to another. Let's say we will be talking about a very easy thing first. So let's say we have a cliff, and from the cliff you drop something down. Now at the top point of that cliff, at the top point of that cliff, that is at the height h, the ball was at rest. So the energy that the ball was possessing was only gravitational potential energy. Now one thing I'm going to tell you, the objects, even us, okay, including any kind of matter, always wants to, or any kind of system also always wants to stay in the lowest possible energy state. That is not like the matters are not like our mind, our greedy mind. If you have money you want more money. It's not like that. Nature wants everything to sacrifice. So in that case, it wants to release the energy. It doesn't want to hold or gain the energy. Always, every single system. Okay, so I'm going to write this as a statement that every single system wants to be in lowest possible energy state. So the very basic example of this thing is that when you have a ball at a height h, your gravitational potential energy is mgh. Okay, but if you put the ball like the downside, what will be the gravitational energy with respect to your ground? It will be 0, because the height with respect to ground is not there. So with respect to ground the energy is 0. So that's why everything in the world, like if you leave, it will go to the earth in order to release the energy. If you talk about if you talk about positive charge, you know that the same charge always repels. So if you bring two same charges together, so you have to give some work, right? So in that case also potential energy will be stored. Like if you have this plus charge and this plus charge, so because of their nature they will they want to go apart from each other. Okay, they want to go away from each other, and then you have to do some work in order to bring any of them. So let's say this one is fixed here, somehow I have make it fixed, and I have made it fixed, and then you want to bring this charge near to this one. So to bring this charge, because they are not going to come simultaneously and spontaneously, because they wants to repel, so you have to give some work. So if you give the work, this work will be stored in this charge as a potential energy, because you are changing the configuration. So when you release that charge again, you will see that again the charge is running away with the it will be running away, so that it can release the energy as kinetic energy. So everything in the universe always wants to stay in the lowest possible potential energy state. Okay, or lowest possible energy state, you better say. So let's talk about this example which I was talking, if you have a ball upside here at a height h, so the gravitational potential energy for this thing will be mgh, right? Because it is at a height h. When you drop the ball, so at first the what you say, velocity was 0, so the kinetic energy was half into m into 0 square, so ultimately it's nothing but your 0, right? Okay, but you will see now that once the ball is dropped, the ball will increase its velocity because it is under the gravitational acceleration, and just before touching the ground, just before, so it just in my drawing, but just before touching the ground, what will happen, the let's say the velocity is v, the final velocity. So in that case, just before touching the ground, just before the impact, the h can be taken as 0 because it's negligible. I'm talking about just before touching. Okay, so we can say that a gpe, that is gravitational potential energy, in this case will be 0 because h value is 0. So we are calculating this gpe with respect to our ground. Okay, so you must tell what is your reference. So gravitational potential energy with respect to ground was mgh, but now it is 0, and the kinetic energy has become half mv square. So you can see one thing clearly, that gravitational potential energy has decreased. So somewhere it has gone, right? Somewhere it has gone because energy always conserved somehow. So and the kinetic energy has increased. So one thing we can see, that somewhere it has gone, that means it has directly converted to kinetic energy. So once the gravitational potential energy is decreasing and the kinetic energy is increasing, that means gravitational potential energy is converting into kinetic energy gradually. So one thing you can say, that the initial initial total energy should be same as the final total energy. So we can easily write this sentence, that in this equation, that mgh, which was the initial potential energy, will be same as the final kinetic energy, that is your half mv square. So if it is so, then from this equation we can find the velocity, the final velocity before the impact. So mm gone, and we can always write this v equal to 2gh. Now this problem we can easily solve using our equation of motion as well, and we can see in that case also v will come this. Let us see that. Let's say we are using this equation, v square equal to u square minus, because plus this case, 2gh. So u square is 0, so we can write from here also 2gh. So one thing you can see, this energy, so this is our energy approach. So many math can be done using our this energy approach. Okay, so in with energy approach we can easily find out some of this kind of maths, and this is our normal equation from equation of motion. So this is from equation of motion, and both of them are giving me same result. So that means whatever we have assumed here, that the conversion of energy is happening, is true, right? So from equation of motion. So this kind of scenario is very much important to understand what will be the final velocity, and you must understand that some places it's very much easier to use energy approach. Okay, that means the energy conservation law. Let us talk about one more thing. Let's say we have a bowl like this. So obviously this is not a bowl, so I'm making it a bowl. and the two sides of the ball is of same height. So if I drop a little ball here, so let me fill the ball. Yeah, so let's say we have a ball right here, and when the ball is at a height h, the ball is possessing only potential energy because the kinetic energy here is zero, right? So it is having potential energy here as mgh, whereas kinetic energy is zero. Now when the ball will roll and it will come to this position, let's say this is my A position, B position and C position, the entire kinetic energy will be like high and the potential energy will be zero, but the kinetic energy will be maximum, that is your half mv square. If is the velocity, and we are again calculating the kinetic in potential energy with respect to this bottom of the bowl. Okay, so now that means the whole potential energy has been converted into kinetic energy, but now because of the inertia, so what is this inertia? This is what you say, the motional inertia. Okay, so because of this inertia of motion, it will not stop here, rather it will go till point C again, where again the velocity will be zero because it is going against your gravity was pulling it down, and it will reach at the same height. Why at the same height? Because if it goes beyond h, so one thing you can see that the energy, potential energy will be higher than in that case. Okay, but that means the initial potential energy and final potential energy will not match if it goes away. Okay, like if it goes more than h, but this is not possible because energy should be always conserved. So like if you drop any marble just from the edge of that bowl, so don't worry, it will not go out of the bowl, because to go out of the bowl it has to reach more, like it has to gain more energy, and which is not possible. Rather there is also friction with the bowl, so obviously it will reach less height than this h. Okay, so this h should be less than that h, but we are not considering it. Okay, just for the sake of the conversion, we are talking about only conversion. So what is happening if we draw a graph here? Let's say this is our height h, and if we draw the graph, let's say I'm using color yellow for the potential energy. So at height at some height h, the potential energy is increasing, like it's like, let's say we are talking about some height here. Okay, wait, I don't think it will be very much good to understand. Let's say this is our energy and this is time, so in that way it will be relevant, right? So at the starting, that means at point A, the potential energy is decreasing because the age is decreasing, but it is important to understand that should it decrease in a linear way or it should decrease some other way. Now one thing you see here, this potential energy depends on h, so PE is dependent on mgh, so it depends on h, and h with time, if I write h, it is ut plus half gt square, right? So ut, let's say it is coming from rest, so ut is gone, so you can say h is proportional to t square. So the graph will not be linear, because that means if I write the PE again, so I can write PE is equal to mg and by 2 g square and t square. So you can see one thing, this is for some instant of time. Okay, so you can see one thing, this is PE is varying with t square, so that means it will not be a what you say, linear, but it will be a parabola. Okay, so this equation represents parabola. if something like y is equal to 4ax square. This is the normal parabola equation. So these are the similarities. So the, like what you say, the graph will be parabolic, so it will be like this. So it will become 0 after some time, and then again it will increase, okay, like this. So it will come to the same line as it was. Acha. But how the kinetic energy will change? So I'm using kinetic energy with this violet, and you can see the kinetic energy was 0 at beginning, but now it is increasing, and kinetic energy is half mv square, where your v varies with t, like this, v equal to u plus at, so you can write directly gt. So v square, so again it's t square, so your kinetic energy is half m g square t square. So in that case also, so both are coming same almost, right? Yeah, so that case also it's parabolic, but it will be like this. So you can see that some points are there where same amount of potential and same amount of kinetic energy is there, so you can calculate this. So there will be two, like time in the case of this rolling ball, where kinetic and potential energy will be same. Okay, so this much was the story about sorry, this was the story about your conversion of kinetic and potential energy. Hope you will watch this video a little bit carefully, and with little bit of what you say, interest. And whatever the question, like other like numericals and everything, we will discuss in our online class. So this is for today, and I will see you in my next video.